In this class, we will continue our discussion of the t-test by looking at a third way to use the t-statistic to evaluate hypotheses of group differences using means. In this class, we'll consider how to use the t-test in a situation in which we measure the same sample of people before and then after a treatment. In the last class, we learned how to test mean differences between independent groups. And by independent groups, we meant that scores in one group were not impacted by scores in the other group. But sometimes we want to measure the same participants over time. In fact, one of the most important questions in clinical research and psychology is not just whether people are better at the end of treatment, but whether or not that improvement is sustained over time. So when we measure participants over time, the group of scores obtained before the treatment are no longer independent of the group of scores obtained after treatment. In fact, we expect scores at the end of treatment, or what we'll call the post-test, to depend on the same individual scores before treatment, or what we'll call the pre-test. So independent variables can come in two types. One is the between subjects independent variable, in which subjects appear in only one level of the independent variable. This is the situation in the independent samples design in which we have participants in either the experimental group or the control group. The second type of independent variable is the within subjects independent variable, in which participants appear in every level of the independent variable. This is the situation in the dependent samples design, in which participants who are measured in the pre-test group are the same participants who will be measured in the post-test group. Thus, we have one independent variable, which we'll call time, with two levels, pre-test and post-test. Because participants in within subjects independent variables are measured during every level of the independent variable, this type of independent variable is sometimes also referred to as a repeated measures independent variable. So let's revise our basic study and say that we select a sample of 30 individuals from the population of depressed adults, but this time we provide all 30 with the new treatment and measure them before the treatment and then after the treatment. So the mean difference we are interested in here is the difference between the means before and after treatment. For the sake of consistency, let's say we continue to use scores on the Beck Depression Inventory as our operational definition of the dependent variable. We can think of our research hypothesis in two ways. One is that the mean BDI scores on the post-test group will be less than the mean BDI scores of the pre-test group. An alternative way to think of this test, and the way we actually compute the t-test for this type of design, is that the mean of all individual differences in scores from pre-test to post-test will be greater than 0. This means when we subtract your post-test score from your pre-test score and then take the mean of all the change or gain scores for each individual, the mean will be positive and greater than 0. We can also present our null hypothesis in two ways as well. One is that there is no difference in the pre-test and post-test means in the population. The other is that the mean of all change scores from pre-test to post-test will equal 0. Because we will compute only one mean to create the t for this type of problem, and by that I mean the mean of the change scores, or what we'll call d bar, and then our degrees of freedom and as a result our degrees of freedom are equal to n minus 1. And here our n is the number of participants, not the number of observations or scores. In this study, we have a sample of 30 individuals from which we'll obtain 60 scores. but our degrees of freedom will be n minus 1, or 29. So the formula we work with changes once again, but only slightly. In the numerator, we will focus on the average of the change scores from pre-test to post-test. This will carry information about the effect of the treatment, or the extent to which the experience of treatment has changed BDI scores. In the denominator, we introduce a different standard error, or the standard error of the mean of change scores. The logic of this standard error is the same as we've discussed previously. Imagine we obtain an infinite number of samples in which 30 individuals, and they all receive a treatment and are given a measure before the treatment and a measure after the treatment. This will result in and we subtract one score from the other for each individual. This will result in a mean of change scores. If the null hypothesis is true, the mean of all the change scores taken from each sample will be 0. And the standard deviation of this distribution of mean change scores will be the standard error of mean change scores, and will be the average distance the pre-test scores might deviate from the post-test scores in a particular sample. So let's work through an example. Let's say we have 30 participants and that the mean BDI for everyone at the pre-test is 24 and the mean BDI at the end of treatment is 12. So for argument's sake, let's also say that the mean of the change scores is 12 and the standard error of the mean of change scores is 3.5. Before going to the next slide, see if you can answer the following question. What is the value of the t-statistic in this situation? What is the critical value? And should we decide to accept or reject the null hypothesis? In this problem, we merely divide the mean change score 12, which we will regard as the treatment effect, or the effect of the treatment, impact of the treatment on the participants, by the standard error of mean change scores, 3.5, which we will regard as an estimate of sampling error, or the extent to which the result could have been influenced by chance alone. So we wind up then with the t-statistic equal to 3.43. From the t-table, when degrees of freedom is equal to 29 and alpha is 0.05 two-tailed test, the critical value is plus or minus 2.045. Because the test statistic exceeds a critical value, we will reject the null hypothesis and conclude that there was a reduction in change scores over time, and conclude that the post-test mean is significantly smaller than the pre-test mean. All things being equal, statistical procedures evaluating the results of experiments with within subjects independent variables will be more powerful than procedures evaluating between subjects independent variable. The short explanation for this is that an important source of error is removed from a within subjects design, namely the way every participant varies from every other participant just by chance. In a within subjects design, as we saw in this t-test, we'll compare your results at the post-test against your results at the pre-test, and my results at the post-test against my results at the pre-test. We are not comparing you with me or either of us with another person in another group. Thus, in a within subjects design, we say that participants act as their own control. When we do this, important error factors are reduced or eliminated substantially, and the result is a more powerful design. One advantage of using a more powerful within subjects design is that we may not need as many participants as we would in a between subjects design to obtain the same result.